In this video, I am going to discuss about the solutions of some important problems regarding the chapter series. So here you can see the first problem. In the first problem, we have to test the convergence of this series 2 square by 3 square plus 2 square into 4 square whole divided by 3 square into 5 square. Then the next term is 2 square, 4 square, 6 square whole divided by 3 square, 5 square, 7 square and so on. So any time whenever you want to solve any problem related to series, it is impulsive that you have to find out the general term or nth term of the given series. That's why initially I have written that let summation un be the given series. Obviously n varies from 1 to infinity, so that un, that is the general term of this series, can be obtained by means of this structure. You can easily understand I have written the at the end 2n whole square, because if you put n is equals to 1 you will get 2 square, if you put n equals to 2 you will get 4 square, if you put n equals to 3 you will get 6 and 6 square. In this way you can continue. Similarly in the denominator portion also you can see 3 square, 5 square, 7 square dot 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 2n plus 1 whole square will be achieved. Now once you have obtained un, straightforward you have to find out un plus 1. Now un plus 1 means whatever you have obtained in un, just simply introduce n is equals to n plus 1 in context of the last term. So that's why you can see 2 square, 4 square, 6 square dot 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 2n whole square, and the last term we have another additional component, that is 2n plus 2 whole square. Similarly in the denominator portion 3 square, 5 square, 7 square, same just like un, and then 2n plus 1 whole square, and finally we have 2n plus 3 whole square, because if you put n equals to n plus 1 here, then it will be 2n plus 3 whole square. Now initially we can start with D'Alembert's ratio test, so that it will be limit n tending to infinity un by un plus 1. This is un plus 1. Now simply you have to evaluate the limit. After simple calculation you will see the value of the limit is 1. I am not going through the calculation, you can see in this particular portion. So whenever limit test provides you the limit 1, that means the ratio test fails to give any particular decision. So technically we cannot give any conclusion on the basis of D'Alembert's ratio test. So here you can proceed towards Raph's test. In case of Raph's test, the basic structure is given by limit n tending to infinity un by un plus 1 minus 1 multiplied by n. So already we have obtained what is un by un plus 1, that is given by this structure 4n square plus 12n plus 9 whole divided by 4n square plus 8n plus 4. So here you can see I have directly used this criteria in the square format, minus 1 which is to be multiplied by n. Again you have to simplify this expression. After simplification you will get certain result, as in this case also we have obtained 1. So that means ratio test also fails to give any decision. So two consecutive tests are not providing you any result. First ratio test, and then obviously we have applied Raph's test. Then we have to go for the third test, which is known as De Morgan and Barton test. So next time we are going to apply this one. So this is the basic structure of De Morgan and Barton test. Limit n tending to infinity un by un plus 1 minus 1 multiplied by n. Then again you have to provide minus 1. The entire portion should be multiplied by log n. Now here simply you can put the values whatever you have obtained in the earlier stage, that is 4n square plus 5n whole divided by 4n square plus 8n plus 4 minus 1 multiplied by log n. Just simply evaluate this expression, then you will get this. Now if you separate the two components, one for the first one, second one for the log n, then you can see I have divided the numerator and denominator simultaneously by n square. So the numerator portion will become 3 plus 4 by n multiplied by log n by n, and the next part, that is in the denominator portion, you will see 4 plus 8 by n plus 4 by n square. Now here you can easily evaluate what is the value of log n by n as limit n tending to infinity. So simply you can see this is an indeterminate form, so you know how to apply the criteria for indeterminate form. Just find out the differentiated structure in the numerator and denominator, and then you will see limit n tending to infinity will give you 0. So irrespective of the first part, the second limit gives you 0, and consequently you can say the result is 0 and which is less than 1, and hence by De Morgan and Barton test we can say the given series must be divergent. So this is the first problem. Now moving on to the second one, we can see using Cauchy's general principle of convergence we have to justify the convergence of 1 minus half plus 1 by 3 minus 1 by 4 and so on. Actually this type of series is termed as alternating series, and in most of the cases we can apply Leibniz test for alternating series to check the convergence, but as mentioned in the question you have to apply Cauchy's general principle of convergence, so we are doing in that way. So first let us define the nth partial sum Sn, that is sum of first term, second term, dot 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 sum of nth term. So if you want to find out Sn plus p minus Sn as required for Cauchy's general principle of convergence, that is sum of n plus p terms minus sum of n terms. So we can write this one equivalent to u1 plus u2 plus dot 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 un, then un plus 1 to un plus p. This part is equivalent to Sn plus p, sum of n plus p number of terms, minus Sn, that will indicate sum of n terms. So just subtract these two portions, you will get un plus 1, un plus 2, dot 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 un plus p. Now if possible, let us assume summation un is the given series, just like the previous problem. Then summation un is the given series implies the general term will be given by minus 1 whole to the power n minus 1 multiplied by 1 by n. Why? Because if you put n equals to 1 here, you will get minus 1 to the power 0 into 1 by 1, that is simply 1. If you put n equals to 2, minus 1 whole to the power 2 minus 1 into half, that means it will be minus half. Similarly, you can get the third term, fourth term, and so on. So after getting un, you can easily detect what is the value of un plus 1. Un plus 1 will be what? Just replace n by n plus 1 in this expression, then you will get minus 1 whole to the power n whole divided into 1 by whole divided by n plus 1. Un plus 2 will be, n should be replaced by n plus 2, that means minus 1 whole to the power n plus 1, then 1 by n plus 2. Continuing in this way, you can find out un plus p, that means n should be replaced by n plus p, so minus 1 whole to the power n plus p minus 1 into 1 by n, where n is definitely a natural number. Now using this criteria we can put all these values, so we can take minus 1 whole to the power n common. After choosing this one as common quantity, we can separate all other structures. Now you can see I have separated them in such a way that first term like this, second term can be grouped by means of a bracket, then again the third and then the fourth and fifth term can be grouped again by means of using brackets. So you can see the entire structure is written in such a way as if it looks like you have subtracted some portion from 1 by n plus 1. Because this part is in modulus, so definitely minus 1 whole to the power n under modulus will provide you 1, and this entire portion will be modified into the form of 1 by n plus 1. So this entire portion can be made less equal 1 by n plus 1, and hence you can say for some epsilon greater than 0 we can choose a suitable natural number for which 1 by n plus 1 must be less than epsilon, and technically that means Sn plus p minus Sn, which is nothing but un plus 1, un plus 2, dot 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 un plus p within mod is less than epsilon, and hence this is true for all n greater or equal m and for all p belonging to set of natural numbers, and hence by Cauchy's general principle of convergence you can say the given series must be convergent. So this is the criteria, or this is the proof for the second one. Now moving on to the third problem, you can see again I have written another problem where we have to test the convergence of the given series. Just observe the structure. Again you have to follow the usual procedure, that is summation un with the given series, where un is the general term given by 1, 3, 5 dot 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 2n minus 1, 2, 4, 6 dot 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 2n. Now you can see an additional term is given 1 by 3, 1 by 5, 1 by 7, and so on. So for this part we have an additional expression, that is 1 by 2n plus 1. Putting n is equals to 1 you will get 3, putting n is equals to 2 you will get 5, putting n is equals to 3 you will get 7. Now consequently you can find out un plus 1. Now simply after obtaining the expression for un plus 1, at first you have to apply D'Alembert's ratio test. After implementing ratio test, find out limit n tending to infinity un by un plus 1. After simple calculation you will be able to find out the value of this limiting structure, which is supposed to be 1. Now that means if you are getting this is equal to 1, ratio test fails to give any decision, so you have to proceed towards Raps test. Now moving on to the Raps test, you can see again I have written the general structure for Raps test, n into un by un plus 1 minus 1, this part should be in bracket. Now simply use the value whatever you have obtained earlier. Now simplify this expression. Now divide the numerator and denominator here by n square so that you can obtain this penultimate structure, which ultimately gives to 6 by 4, that is 3 by 2 under simplified form, which is greater than 1. And that means if this is greater than 1, So by RAPS test the given series must be convergent. So in this problem you have seen, although ratio test fails to give any conclusion, but with the help of RAPS test you are able to generate the criteria that the given series must be convergent by using RAPS test. Now we have another important problem. Sometimes we are asked to find out the justification regarding absolute and conditional convergence of the certain series. So here the series is given by this -1 whole to the power n minus 1 by n to the power p. So intentionally I have written the given series can be written in the form of summation of -1 whole to the power n minus 1 into un. Obviously un is what? 1 by n to the power p. P is such that greater than 0, we are considering this one, so that n plus 1 whole to the power p must be greater than n to the power p. Because if you split this one by means of binomial theorem, it will contain more terms than that of n to the power p. So just take the reciprocal, it will give you the reverse relation. But this one is nothing but un plus 1, this is un, so un plus 1 must be less than un for all n belonging to n. And also you can see, as you operate n tending to infinity, so this structure will tend towards 0. Now remember, there was a necessary condition, if limit n tending to infinity un is equals to 0, then summation un is convergent. So this is an alternating structure, because you can see if you put n equals to 1, 2, 3, 4 etc., then gradually the sign will be altered. In the first part, if you put n equals to 1, you will get positive, n equals to 2 will give you negative term, and so on. So that's why we can apply Leibniz test for alternating series, and by means of which already we have seen this structure is monotone. So technically we can say, in fact this is monotone decreasing structure, so we can say by Leibniz test for alternating series the given series must be convergent. Now to verify the absolute convergence, simply put modulus over this structure, then it will be reduced to summation 1 by n to the power p, which is definitely convergent for p greater than 1, because we know this is the common form of p series. So p series is convergent for p greater than 1, whereas it should be divergent for p less equal 1, and hence the given series is absolutely convergent for p greater than 1. But if you consider the modulus, then it will also become divergent for p less equal 1, whereas instead of, if you don't want to use modulus, instead of not using modulus, we can see from the original structure it is definitely convergent. So the structure is also conditionally convergent for 0 less equal p less equal 1. Now here I would like to make one comment. Conditionally convergent means initially the structure is convergent, but if you impose modulus over it, then it may be divergent. Here you can see originally the structure is supposed to be convergent, but whenever you are imposing modulus, it becomes divergent for p less equal 1, and because p is greater than 0, then we can say the structure must be conditionally convergent for 0 less equal p less equal 1. So these are few important problems. If you have any doubt, you can give your opinion in the comment box, and obviously if you have any other problem, you can directly contact me via comment box, and hopefully all these problems are useful for your examination. Thank you.